That's why I said that.
There was gonna be a princess too.
So let's spend at least 15 minutes in this current, resistance, and resistivity, which will lead us to electric circuits. Okay? So now we have charges that are moving, and when charges are moving, if you count them, if you count the charges that pass by you in a certain amount of time, we call that the current. So it's the amount of charge that passes by per unit of time. So current. It's basically charge over time. Charge over time. And so it would be, the units would be amperes. 1 ampere is 1 coulomb per second, right? An ampere has the symbol A, so 1A. Problem is area also has the symbol A. We will use area right now. Yeah, so fortunately the symbol is A. With little, yeah. Whenever there is confusion or possible confusion, I would write the whole word ampere. Yeah. Just like coulomb looks like C capacitance, but if there is source for confusion, write the whole word. Okay. So that's an ampere. So we need to give it a symbol. So for current, it has the symbol I. So the average current is the amount of charge that passes by per unit of time. That's the average current. Usually the current is steady, but if it's varying, we have the average. If you want the instantaneous current, it's dq/dt. Okay, sounds good. Then there is what's called current density. Current density is the amount of current per unit of area. Because usually current is flowing across, right? In a wire. So here is a wire, and the wire would have a cross-sectional area A. Area is A. That's what I said. The current has amperes. The area is A. So the cross-sectional area is A. In that case, we have the current density. It has the symbol J, and it's the current over area. The current per unit of area. Yeah, J. Not joules. The current density is, yeah, see the letters are coming back to mean different things. Yeah. Yeah.
So that would be like amps per meter squared.
Yeah, per square meter, yeah. Yeah. So, yeah, that's a good point that we stated. The units for current density would be amperes per square meter, right? Amps. Amps means amperes, right? Amps, amperes per square meter. That's the unit for current density. That's J. Now the current density may be uniform, it may not be uniform, and it's also a vector. The current density, it could be a vector. Yeah, we usually don't have to deal with the vector, but I'm going to state it anyways. So if it's, in general, the current would be J dot dA, and then you have to integrate over the area. But if it's uniform, and it happens to be parallel to the area, then you would just have J times the area. J times area is current. But sometimes J is not constant. We will have problems where it's not constant. You have to integrate. Yeah.
How is J a vector?
It has a direction. The current can flow this way, it might change flow. Yeah.
So would it ever come at the area like that? How would it get
It's possible. Yeah, it is possible. Let's. I have an example where we can look at. Yeah.
So there's only one type of density which is only depends on the area, no volume, no.
Yeah, because the current you have to cross an area. Yeah. In
Oh.
3 dimensions. Yeah. Yeah. So that's the current density. So let's think about charges moving and what happens. So now, if you have a copper wire, you would have electrons moving, right? They're free to move. It's a conductor. And so in general, you would have charge carriers. They could be like charged ions, right? I think for sodium, I think you have Na plus, it would be +1, right? Yeah. Okay. Okay. Yeah. So it could be an ion that's moving, or it could be just an electron, right? Or some positively charged. So in general, whether it's copper or something else, how many charge carriers do you think you have per cubic meter? A lot or little? A lot per cubic meter is a lot. So do you think it's 10 or 15 or 100 or thousands or many more than that? Many more than that. So the number, the number of charge carriers, or little n, would be the number density. Number of charge carriers.
Wait, can we make it in current or something?
Per volume. Per volume. For example, I'll just to give a number for let's do copper. N is about 8.5 times 10 to the 28 per cubic meter. So cubic meters to the -3. So a lot. Okay. So in general, it's something times 10 to the 28 or 27 or something. A lot. Okay. So this is the number of carriers per unit of per volt.
Sorry, what is N?
And number of charge carriers per unit of volume. It's the number of density. So maybe, let's say I have the number of sodium ions per cubic meter would be some large number. So the current is charges moving, right? So in a cubic meter, how many do I have? A lot. And this number tells you what it is. Okay. So you get it from some data. Yes.
Before we go over this question later, but how actually is the electron going through the copper atom? Is it like ionizing them for like milliseconds and then moving on to the next ionized while that one collapses, or
Usually you have 3 electrons per atom, and they are not bound to any electron. So they not bound to any particular atom. And so if you have 10 to the 28 atoms per cubic meter, so you have that many electrons per cubic meter that are free to move.
so the electron are just kind of attracted to the proton of like a specific copper atom, and then they'll like move on to the next one?
Yes, they're free to move. They're not bound from one. They're not bound to a particular atom.
Okay.
Yeah. Jeff, I think
Yeah.
you still have questions? You're good. Okay. So let me. So you have a lot of charge carriers that are moving, and for current, okay, current is the charges. The charges that move when we say a current I is the positive charges moving. Okay? It's the positive charges moving. Okay. So let's say, let me erase these for a moment. Let's say at t equal to 0, I start counting how many charges pass by. So after a delta t, right, the atoms are moving, right? The charge carriers are moving. Imagine positive charges are moving to the right. And so I'm here and I'm watching them move, right? And I'm counting them. So let's say at t equal to 0, I start counting. The very first one that enters at t equal to 0 after time delta t, it will move here, right? It will have been here. So the very first ones that have entered there here, the very last one to enter at t equal to delta t is here. So the amount that have passed me, this is the first, this is maybe the wave that came after it, and then the ones that came after. So they fill up this gap, delta x. That's how many I have passed by. And this delta x will be the speed, the average speed with which they are moving this way, times the time delta t. And this speed is given the subscript d. It's called the drift speed. Okay?
To what?
Vd is called the drift speed. That's the speed on average with which they progress to the right. So the question is, how many charges have passed by? How many charges have passed by? The answer is delta q, and the number of charges that have passed by. I take the number of carriers per volume. Right? The number of carriers per volume. If I multiply by the volume, what do I get? The number of carriers that have moved, right?
Yeah.
And then each carrier will have a charge q. Maybe one electron, or a plus e, maybe twice plus e. So I would call it q. Each carrier would have a charge q. This q here we will take to be little e in a second. But for now, I'm going to leave it as q. And what's the volume there? What's the volume of that little thing?
8 times.
The area
8
times
times delta x.
times delta x. Okay, good. But delta x is v times delta t, right? Drift speed times delta t. So delta q over delta t will equal to little q and a v drift. What's delta q over delta t? That's the current. Now J, which is the current over the area, will just be little q and v drift. Now let me write here. We usually have q is just equal to v. Each charge carrier has just one plus charge. So that means J will just be E little n times V. So next time we'll start from here, fresh, and then we will continue. It's a short chapter, so next time we'll finish this and get to the next one, which is circuits.